Hi, Algebra 2. We're moving ahead today to Lesson 6.2, where we're going to continue to look at exponential models. You can see the objective today is I can write exponential models in different ways to solve problems. As always, we like to kind of start by talking about specifically what we're doing today. And in day 1, we're going to identify rates in exponential functions. We're going to talk about something called compound interest. And we're just going to introduce this idea of Euler's number and start talking about what that means. Tomorrow, we'll start talking about continuously compound interest. All right, so let's make some connections. It says one is studying exponential growth of bacteria cultures. Each is carefully controlled to maintain a specific growth rate. Complete the table to find the number of bacteria cells in each culture. So culture A has an initial amount of 10,000, growth rate per day is 8%, and time is 1 day. So using what we did yesterday, we would just do 10,000 times 1.08. So that 1 plus r to the t, which is 1. I type that into my calculator and I get 10,800. Okay, in the second one, this time it's $10,000 again as my initial amount. But this time it's only 4%, so I use 1.04, but to the second power. When I did that, I get 10,816, I think. Might have been 810. I can't really read my last number. The third one, again, 10,000 times 1.02 to the fourth. That time I got 10,824. And last but not least, I did 10,000 times 1.01 to the eighth. And that one gave me 10,828. Now it says, what is the relationship between the daily growth rate, so that's this table, and the time? Well, what we can see is that if we actually multiply these together, all of them give me 8%. Okay, so we changed the growth rate, but every time the growth rate changed, we actually changed the time. So we always got 8% or a decimal of 0.08. Now it says, would you expect a culture with a growth rate of 0.5%, so like lower on this table, so 0.5%, and a time of 16 days. So again, I'm still multiplying together. I still get 8% to have more or fewer cells than the others in the table. Well, let's look at the final number of bacteria. Even though my growth rates are decreasing, my times are increasing, and again, the overall multiplication is the same. So that's still the same here. So this is still going down. Look what's happening with my final bacteria. These are actually going up. Okay, so as the percentage decreases, but the number of days goes up, these grow at a faster rate. So I would actually expect the next row to again have more cells than the previous table because they keep getting bigger. Okay? All right, so that's a connection. But now let's look at something we're going to do with this. Now this again takes what we did yesterday, but it adds a twist. And sometimes this twist can be kind of confusing. It says in 2015, the population of a small town was 8,000. The population is increasing at a rate of 2.5%. So using what we did yesterday, this would be my initial amount. Okay, so that's my initial amount. This is my growth rate, which is R. And it's exponential growth, okay, because it's increasing. And we want to find the monthly growth rate. Okay, so we're still using that, but they actually want us to find a monthly growth rate. Well, when I write my equation, I would have y equals that initial amount, which is 8,000, times 1 plus r, because it's growth, so 0.025. Technically, it would be to t. This is if we were in years. Okay, so that was yesterday, if it was talking about in years. The problem is this wants it in the monthly situation. For me to convert years to months, I would need to multiply by 12. Okay, so if I multiply t by 12, that converts it to months. Problem is I can't just all of a sudden multiply the exponent by 12. So to make it a legal math move, as I like to call it, those of you who have me, if I'm going to multiply t by something, I have to multiply by something equal to 1. So we're actually going to multiply t by 12 over 12 to get it into months. Okay, and we'll talk about what we'll do next. I'm actually going to change this now to 1.025. And again, my first step, if I want it monthly, is to change it to 12 over 12t. But again, we said ultimately we just want t times 12. So now we're going to use our power to a power rule, and we're going to break that apart. I can rewrite 12 as 1/12 times 12t, right? I'm allowed to do that. Well, if I want to, then I can move that 1/12 to inside the exponent because this would tell me to multiply. We're using some of those properties we've used in the past. 0.025 to the 1/12 to the 12t. So I've finally gotten that 12t by itself on the outside. Now this I'm allowed to type into my calculator. So I just typed in 1.025 to the exponent of 1/12. That gave me 1.00206 to the 12t. Okay, so this is actually the equation for growth at a monthly rate. But now the problem is they actually want me to figure out my R value. Okay, so my monthly R value. Well, yesterday we talked about if we know what B is, so B is 1.00206, and we did this yesterday. Okay, so we said, well, we know B is 1 plus R in this case. So if B is 1.00206 equals 1 plus R, to find out the R, I would subtract 1. So I get 0.00206 equals R. Okay, so R, a monthly R, that's the difference, is 0.00206. As a percentage, if I move this decimal 2 places to the right, I get 0.206%. That is the amount of increase per month. So it's the increase per month. Now again, it seems a little odd. The new part is understanding that you still set it up the same as you would before, but if it's changing, if we want the monthly growth rate instead of the annual growth rate, which is the 2.5, we have to do this to our exponent. You've got to break it apart and figure out what your new B value is for a monthly rate. Once you have that new B value for the monthly rate, then you use the formula like we did before. Okay, so a little twist on kind of what we did yesterday. All right, so I want you to pause this and see if you can at least get started on it. This one says the population of a small town is increasing annually by 1.8%. What is the quarterly rate of population increase? So again, pause it and see if you can at least kind of write out what you think it might start as. Just as a tip though, if it doesn't tell you population, like what it starts at, I always just assume 1. Okay, so 1 times something. So start by doing the annual. Hopefully annually you did 1 plus 0.018 to the t. Okay, so that's where we start. And now I want you to do that weird thing with the exponent we talked about, but this time it's quarterly. Last time it was monthly. See if you can figure out how you might change it when it's quarterly. Pause the video and write it down. You should have done 1 times 1.018 to the 4t, but over 4. Remember, we have to basically multiply it by 1, but we need it to be 4t in the exponent. I'm going to ignore this one now. So that gives me 1.018. I'm going to pull the 1/4 inside so that it's just to the 4t on the outside. Type this into my calculator, and I get 1.00447 to the 4t. Okay, so that is my equation for a quarterly rate. But now if I need to find B for the quarterly rate, remember my R for a quarterly, so my B is 1.00447. We know that B, when it's increasing, is 1 plus R. So again, I would substitute in 1.00447 equals 1 plus R and subtract 1. Okay, so you could always set it up like this, and we do in fact get 0.00447 is our R, but we always write it as a percent. So it increases because we're talking about percent increase. This moves over 0.447% quarterly though. That's the key, is we are no longer annual when we switch it like this. Okay, so that's the first thing you have to be able to do from today. And then the other thing we're going to talk about is this thing called compound interest. Okay, so when interest is paid monthly, the interest earned after the first month becomes part of the new principal for the second month, and so on. Interest is earned on interest already earned. This is compound interest. Here's the key. The compound interest formula, you want to get this in your notes, is A equals P times 1 plus R divided by N to the NT. Okay, so this is kind of building off of what we just did. Now, when we look at this, You also want to make sure you know what the variables represent. P is the initial principal, or the amount invested. R is still the interest rate written as a decimal. N is the number of compounding years per period. And T is the number of years. Okay, the A on the left is the total amount. All right, so let's look at an example. So Tamira invests $5,000, so that's going to be my principal amount, in an account that pays 4% annual interest. So we convert that to a decimal, so my R is going to be 0.04. How much will there be in the account after 3 years, that's T, if the interest is compounded annually? Now, when we're figuring out what N is, remember N is the number of times compounded per year. Sometimes students get confused by the 4% annual interest. This word annual doesn't actually matter. It's compounded annually. This is the word that matters. If it's compounded annually, that means N is 1. Then it wants me to find semi-annually. Well, that's 2 times a year, so N is 2. Wants me to figure out quarterly. That's 4 times a year. And finally, monthly is N equals 12. So it actually wants me to do 4 separate problems within this one. Let's do the first couple together. So I take A equals P, which is 5,000, times 1 plus my interest rate, which is 0.04, divided by, this is my annual, okay, well, maybe you should keep track of that, annually over 1 to the 1 times T, which is 3. Now I'm going to show you in just a minute how to type all of that into my calculator. But once I have that all there, I should be able to type it all in, 5,624.32. You will have to be very careful with how you type these in. So you do want to practice that as we go. When we do semi-annually, I have A equals still 5,000 times 1 plus still 0.04. The only thing that's changing is the N, which is in this spot and this spot. Semi-annually is twice a year, so 2 to the 2 times 3. Again, I would type that into my calculator, and I would get $5,630.81. I do want you to pause the video right now and see if you can write the expressions for quarterly and monthly, so change what you need to change. But then I also, during that time, want you to try to type these into your calculator to see if you can get the right answers. So I'm going to pause. I want you to pause the video, do that, and then come back, because I will show you the answers, and then I will show you an example of how you type this in. Okay, so quarterly, you should have had A equals 5,000 times 1 plus 0.04 divided by 4, because it's 4 times a year, to the 4 times 3, which was $5,634.13. And finally, last but not least, monthly, you should have had A equals and typed in 5,000 times 1 plus 0.04 divided by 12 to the 12 times 3. Typically speaking, students don't have a problem setting these up. They have a problem typing it in. So if you got 5636.36 and those two correct, you probably are okay with your calculator. However, I do want to make sure I show you how to type this in so those of you who got those wrong can make adjustments. So I'm going to show you how I typed in the quarterly one, which was the first one that you guys had to type in. I would obviously just type in 5,000 like you normally would, parenthesis 1 plus. That part's straightforward. It looks exactly like it is. But remember, now I have to do 0.04 divided by 4. Make sure you put that in a separate set of parentheses. So I go parenthesis 0.04 divided by 4. Now the first parenthesis closes up this fraction, but now I need a second parenthesis to close the bigger parenthesis. So you actually have to have a double parenthesis there. Okay? Now it's to the power of. Now you could do 4 times 3, and you know it's 12. Otherwise, it depends on your calculator. This calculator actually puts everything in the exponent, so I can do 4 times 3. Oh, not a negative 3. 4 times 3. And so that's going to make it 12 in the exponent. But one thing to be careful of, in the calculator that I have, an older version, I actually have to put parentheses around it. It won't matter either way on this one, but if it just shows the caret key, and then it's in the same line as this, then you'll need parentheses if you don't just change it to 12. Okay, but when I hit enter, you can see I got the 5,634.13. If you put 0.12 on this on Pearson, it's going to be wrong. You're always rounding money. If it's a 5 next to the number you're rounding to, You want to make sure you change that to a 3. Okay, and then the other one you had to do was 5,000 times 1 plus, and again, in parentheses, 0.04 didn't change, but it's divided by 12 now. Okay, I close that parenthesis for the fraction. I close the second parenthesis, which is the outside of the 1. Then I go to the 12 times 3 power. And I'll show you on this one how you don't need those parentheses because it's all in the exponent. So that's how you get the 5,636.36. And again, next to the second decimal place was a 9. That's why I rounded up. So now that we've reviewed how to put it in our calculator, I want you to try this problem on your own. $3,000 is invested into an account that earns 3% interest compounded monthly. What is the value of the account after 10 years and the value of the account after 100? So pause the video, write out your formulas, and then type it into your calculator to make sure you can get the right thing. All right, for this one, you should have had 3,000 times 1 plus 0.03 divided by 12 because it's monthly to the 12 times 10. Okay, so when I typed that into my calculator, I got 4,048.06. So make sure you know how to type it into your calculator. For the other problem, you should have done 3,000 times 1 plus 0.03 divided by 12 to the 12 times 100. So the only thing that changed in this example was the years. Obviously, the more years you have it in, the more money you're going to make. So this was actually $60,031.45. So it grew a lot in those next 90 years. All right, so those things are the things you have to be able to do in your homework tonight. The last thing, just for time purposes, is that we could use this idea to introduce ourselves to this thing called Euler's number. Okay, so this is really, you can just watch, you don't have to write this down, but it says consider an investment of $1, so that's why this is a 1, into an account that pays 100% annual interest, so that's why this is a 1, for 1 year. Okay, so that's why this is a 1. So basically, we're putting all 1s in. The only thing that's going to change is the number of times per year that is calculated. Okay, so it says gives amount in the account after 1 year for a number of compounding periods and find the value for all these values, or value, find all these things in the table. So for this one, it wants me to do 1 times 1 plus 1 over 1 to the 1 times 1. Okay, I typed all that into my calculator and I got 2. Again, you don't have to type these in. This one, it wants me to do 1 plus 1 over 10 to the 1, or 10 times 1. When I typed that in, I got 2.5937. This one wanted me to do 1 times 1 plus 1 over 100 to the 100 times 1. When I did that, I got 2.7048. Now I kept going. When I plugged 1,000 in, I got 2.7169. This one gave me 2.7181. This one gave me 2.7183. Okay? So it really just wanted us to look at the pattern here, and it wanted us to notice about the amount as the number of compounding periods increases. Well, what I see is the n's are getting very, very, very big. Okay? But let's look, so as n keeps increasing, what's happening to our answers? Well, it went from 2 to 2.5937 to 2.70, 2.7169, 2.7181, 2.7183. What's crazy about this is it's not growing that much. The answer, the amount, is not growing that much. Okay? The value of the amount count remains very close to 2.718. Okay, so both of these actually were 2.718 if I rounded. Okay, that's not a coincidence. The reason that that happens is because it's actually a special number. It's kind of like pi. It's a special number called the natural base. And tomorrow we're going to start using the natural base. It's going to be the E on your calculator. Okay, and that's what we're going to use tomorrow. Okay, so this slide was just an intro. You don't need it. We used the formula. That's why it fell at the end of today. But tomorrow we'll talk about how we're going to use this new special number called E. Okay, all right, go ahead and work on your 6-2 day 1 homework. Thanks.